M and J.
M and J. Okay, very good. Do you have a Rayleigh's dissipation function?
Yes.
From?
Damper C.
From the damper C. Okay, very good. And then you also have potential energy, right? From the K. Okay. So how do we actually write? So in other words, it has all the terms, yeah, except for maybe one of the term is 0, as I told you. So the way we write it is, first you write for the kinetic energy. And the kinetic energy that you have two, right? You have the mass and also you have the J in this case. So for the J is because they already asked you in the question, they want you to actually write it in terms of X. So you want to actually change whatever term in terms of theta is in terms of X. So you know K and C are all linear systems. So you're going to have the expression in terms of X. What is not linear is the J, because your J is in the form of half J theta dot square. So in other words, you have to convert your theta in terms of your X. So if you look at this, how do you convert that? So you can actually take a look at this part here. Is like your small triangle, okay, that describes the X is here, which correspond to the displacement of your K and your C. So they also draw it here, but basically this X is basically this displacement X here equals to r theta, because r is the radius of this, because this actually turning, it turns at an angle of theta. So this red triangle describe the relationship between your X and also your theta, which is X equals to r theta. Yeah, so that's how you get these expressions, X equals to r theta. All right, and this X corresponds to the displacement for the mass and for the K and the C. Okay, it's all connected. Very similarly to what you have if you have a mass, spring, and damper. They share the same displacement, which is X. So similar as in this case. So for the G, then you have to convert your X in terms of your theta in terms of X. So your theta is X over R. So then you get these expressions. So once you have this expression, you can just write your normal kinetic energy equation, which is half mx dot square plus half j theta dot square, which is already transformed into x term. So that's how you get this expression. Okay, then you go to the potential energy. You just have the K, so it's easy. So have kx square, and your damper, you have xc dot square. So that's very, very easy. Maybe I blow it up a little bit. Yeah, okay. So if you look at, yeah, then what you need to do, you've done basically. So easy, isn't it? You don't have to think about the free body diagram. This is a single degree of freedom system. You don't need to think about relative displacement. So you just identify the elements, the K, the C, the M, the J here. Then you just substitute into this formula. You have your T, U, and R. Basically, we use the term, this R Rayleigh's dissipation function was D just now in your original equation, and your V is your U. All right, so then we just write it. The first part is you take the partial derivative of your expressions T. So I already put it up here. Okay, maybe we can focus on this. So you put the T in there, and then you have your U, and then you have your damper expressions. your stiffness expressions, your damper expressions, and your mass and the J expressions here. Okay, so we know already this one is, there's no term of X here, so that is 0. So you only have 3 terms, 1, 2, and 3. Okay, the second term is 0. So how do you differentiate this with respect to X dot? Easy. So you just times 2 times 1/2 m plus j over r2 x dot. Then you differentiate again with respect to t. So that's easy. You just put the dot. You just put another dot there. So that's the whole expression here is this part. Do the same thing here. 2 times half kx. You get just kx. 2 times half cx dot. You just get cx dot. Then what you need to do is, in this question, they ask you to find the omega n. So omega n is just your square root of k over this equivalent mass equation, which is this part here. So you get the answer. Any question? So this is fairly easy, yeah? Any question? Maybe I ask you why it looks like in the first place it's kind of like 2 degree of freedom system, but it collapsed it into 1 degree of freedom system. So that's why you are only you only need to differentiate it with respect to x. That's what the question asks you. Okay, good. Are you guys good? All right, easy peasy. Then we go to the next question. So that is the easiest part of Lagrange, which is only singular degree of freedom system. Okay, let me show you another system, slightly complicated. Okay, this is semester 1, 1920. Let me hold on, yeah, I haven't shared the screen. Okay. All right, this is semester 1, 1920. You can see, like the first question, they ask you to use Newton's second law. So normally the first question is singular degree of freedom system. Then only you go to the second question is the one that you want to use Lagrange. In this case, they ask you for 2 degree of freedom system. So depending on the semesters, we just change. Sometimes you are asked to use Lagrange on the first, on the 1 degree. Sometimes we ask you on the 2 degree. Yeah. So that's why I said just make sure you know how to solve using Lagrange to solve both problems. Yeah, 2 and 1 degree. So in this case, let me adjust this a little bit. Okay, maybe that's better. Okay, so they give you this figure. It consists of 2 pulleys. And you know, this is, you need to determine somehow this relative displacement of K. But you are asked to use Lagrange. They gave to you already. Both pulleys rotate in a counterclockwise, theta 1 and theta 2 respectively. You may assume that both springs in the system are massless and the cords that which pass over the pulleys do not slip. It's just saying that you don't have to worry about if the pulley has mass in that sense. Sorry, not the pulley. The springs in the system are massless. So the springs are as normal spring. You don't have to consider the mass of the spring, which is always the assumptions that we have in throughout the course. Yeah, but the pulley will experience rotation in this case, pure rotation, and that's why you have in terms of theta 1 and theta 2. You also have these masses here. And you can see that you also have external input F naught sine omega t. So that's a handful of things to look at, but at the end of the day, you need to come up with the equations of motions. There'll be two equations to this. Okay, so maybe you know the questions. We go in terms of counterclockwise, there's a drawing already there, so you don't have to worry about that. Let us take a look at how we solve this problem. I know maybe it's a bit lengthy, but don't worry. If you know the steps, it shouldn't be that difficult. All right, maybe you have to take note that when you have these two figures, sorry, okay, yeah. Okay. Salah pula. Where is the file now? It's gone. Oh yeah, here it is. Okay. Got the wrong one. Here it is. Okay. Nice. All right. So when you take a look at these two figures, it should be good news is you don't have damper, so you know you don't have expressions. You just have the J as well as the, well, you have Jm, which goes to your kinetic energy equation, and then you have the case. Yeah, you have two case here. But what you need to do first before you want to write the kinetic equations and the potential equations, you only have two type of equations, the T and the V. Is you need to make sure you know how to write your relative displacement. So in the problem, they already, oh, sorry, tadi dah. Thank you for recording it. I totally forgot about it. Thank you. So you can see, okay, how do you start a problem and think whether that particular element needs to have relative displacement or not? You always take a look at the K or the damper, whether it is in between two positions. So the one that has two positions are basically your K here. The one that's fixed is easy because it's basically Kx minus 0. So you don't have to think. So this K is fixed. So you don't have to think about relative displacement. You just need to make sure that the assumed direction is in the way you write it, that you assume it moves in the same direction as the assumed direction. Yeah, so you have that one taken care of. But this one you have to write in terms of relative displacement. Maybe just looking at it at the first glance, you don't know. You have to think whether theta 1 minus theta 2 or theta 2 minus theta 1. So that one you have to figure out. At the same point, this K, okay, is located at different, because this K is linear, remember. So if you want to draw the small triangle, is basically this displacement for the K is here. This side, and it is at the radius r, theta 1. Whereas this side is at r, theta 2. So this one, if you want to draw the small triangle, is basically this triangle here, okay? This is the triangle. All right, so I hope you can see my cursor. Same as this one, the triangle is the displacement x and r, okay, and you also have the theta. Okay, so this is the triangle over here. So that's why the way you write it is basically, this is a linear spring, so it's supposed to be kx1 minus x2 or x2 minus x1, but now you have to write in terms of theta 1 and theta 2. So the way I write it here, so it's easy. You know that x2, theta 2 and theta 1 is counterclockwise, as I showed here. So think of it physically, okay, what happens to your mass here and your spring. So your mass here is x1, And you also have your spring, not spring, yeah. So this mass also x2. So you always have to think of it physically, what happened to the system. So you can imagine this whole thing move, okay, although you have this F naught here, you're assuming this x2 goes up and it goes round like that, yeah. So in that sense, that means your K, in this case, we are assuming when theta goes that way, so you have this K is in tension, yeah. Um, then actually, if you want to assume it is in compression, also can, but in this case, I assume tension. So you can only assume either tension or compression. So in this case, it's in tension. So you can draw the figure here. So in that sense, you just draw the uh, action reaction if you want. But if you want to go straight and assume it's a tension or a compression, so you would write it in this way. So you take a look at which side is positive. So you see that theta 1, okay, belongs to this side of your theta. So this is actually positive, but theta 2 over here, or I want to call it R2 theta 2, basically, sorry, R theta 2, yeah, these radius are the same. So R theta 2 is basically negative in this sense, okay, because it goes, if you go from the pivot point to this arrowhead, it's actually clockwise, so it becomes negative, okay. Or you can also see it's at an x as well, so it becomes negative. This one is positive. All right, so we've done with the relative displacement. It doesn't matter if you don't want to draw this arrow or whatever. First thing, you have to look at which spring experience relative displacement, okay, which located in between the two positions. So this is the one. Then you decide tension and compression. In this case, we decide as tension, so we put it as in that equation. All right, so then the next one, oh yeah, I do have a figure here just to show you the relationship between x1 and x2. So this is basically kx1 minus x2, right? But I wrote everything in terms of theta. Then you go ahead and look at your equations here. So I have this drawing here. You have to write for all, yeah, the j. So you have two j's here, which experience totally rotational, pure rotational. So that's why you have these two terms here. You have for j1, theta 1, okay, and then the j2 theta dot 2 square. You also have the mass, okay, so have mx dot 1 square, okay, and mx dot 2 square. So I'm assuming here the mass has the same, it's the same mass and the same k, okay. Then we have to write it in terms of theta. So this is maybe another tricky part. You have to convert everything in terms of theta. So you can write it as in this equation. So your x1, so I have the relationship here, your x, which is basically your displacement for your k, okay. This one is supposed to be kx1, isn't it? But now your x1 here in relation to theta, it is at a distance of r. All right, so if it's at a distance of r, the way we write it is x1 r theta 1. So do the same thing for your x2, okay? Your x2, because this x2 belongs to the m. So this x2 now, okay, this is the slightly tricky part. So this x2, okay, which is actually corresponding to this displacement over here. Is basically, this is the triangle, so it is at a distance of r2. Okay, so sorry, 2r. 2r. So I gave here, yeah, the radius is 2r, not r. So this m is located at 2r, which correspond to this x2. So if you want to draw this triangle, is basically located here. So it's kind of like a triangle here, yeah. So that's how we draw it. So x2 is equal to 2r theta 2. Okay, 2r theta 2. X1 is r theta 1. Any questions so far? Are you all right? Are you guys okay? Okay. So what you need to do is, yeah, so after that you just substitute x dot 1. Okay, x dot 1 means r theta dot 1 square. So don't forget the square. And a lot of maybe students make slight mistake, because when you square it, you have to square the whole term. It means you have to square the r. You also have to square the theta dot. So in this case, that's what you have. You have r square and theta dot 1 square. Same for this one. X dot 2. Okay, x dot 2 means 2r everything square, theta 2 also square. So that's how you get 4r square theta dot 2 square. Okay. So then you write for the springs. So remember, you only have two springs here. You have the K, both are Ks, yeah? You have these two springs, so you have to write the equations for the two springs. So the one on the left is have Kx1 square. Maybe I put this at the next of it so that you can see. Yep. Okay, yeah. So this side here, you have kx1 square. So I'm just calling it as x1 and x2 here so that we know. So you have another part is just this k. So this k is the one which has the relative displacement just now. So you just write it everything square. Yeah. So we try to write everything in terms of theta. Okay, so you can see, because in the problem they want to express it in terms of theta. All right, so the one with the x1, so you already have this relationship. So x1 is equals to r theta 1. So that's why you have here your r has to be square, your theta 1 also has to be square, because this whole thing is square. So you have those expressions. So you've done with that. And then you have Q. Your Q now is F naught sine omega t. Okay, what you need to do with this, because everything we want to express in terms of theta, then we write it because you want to write as theta 1 and theta 2, isn't it? So everything has to be in theta. So that means your input force will become moment, because all these are summation of moment, yeah, in terms of you have to times this distance here. So in this case, your F naught, you have to times the distance here, which is 2r. So it's not just F naught sine omega t. If you are doing a linear system all in x, then you put in terms of F naught sine omega t. But now you put everything in terms of theta. You have to put it in terms of moment. So in this case, okay. Anybody wants to answer this question? Why is it negative? Anybody? Why is the moment is negative? Yeah, because you can see here it's opposite. So basically you're assume, because all the theta is counterclockwise. If you want to look at it linearly, x2 goes up, so your F naught goes down. So your force is negative, but you have to times the distance to convert it in terms of moment. All right. So then, okay, after you've done, so this is an example of how you get a full equation. You have your T, you have your V, you have, yeah, you don't have D, but it's kind of like, it's quite handful here because you have like 4 expressions for your T and your V. So you do the same thing as what you would do just now. You have these 2 columns for theta 1 and theta 2, okay? So you have the first expression for your Lagrange equation here. You have the first expression, which is you differentiate your kinetic energy in terms of with respect to your theta 1 for this column, and another one is theta dot 1 and theta dot 2. So you do the same thing. So first you look at the expressions with the theta dot 1. So you just have this and this. You have 2 expressions there. So you just times 2 times 1/2 j1 theta dot 1. So that's why you get j1 theta dot 1. 2 times half, which is 1, and then you have mr square. So this square is not the same as this square, so you have to write it down again. Mr square theta dot 1. So that's why you have this. Mr square theta dot 1. So you've done. Then you do the same thing for your, with respect to theta dot 2, basically. Okay, so this is the expressions with respect to theta dot 1, theta dot 2. So when you look at theta dot 2, is just this one, this expression, and this expression. These 2 expressions will become 0. It's a constant because you don't have theta dot 2 there. So you have to go here, 2 times half is 1, so you just left with j2 theta dot 2. So that's why you get this, and this one is just 4mr squared theta dot 2 because you're 2 power of 2 times 1/2. All right, easy. Then for with respect to t, it's easy. You just put extra dot there. So now you have theta double dot 1. Theta double dot 2. Okay. Then the second part, in your kinetic energy, there is no theta 1, there is no theta 2. Yeah, all theta dot. So that's why the second equation, second term is equal to 0. Then the third term is also equal to 0 because your D, there's no damper. Okay, then you take a look at your kinetic energy. So your kinetic energy, you have your kinetic energy here. If you look at that, it's just half, 2 times 1/2. So you just write the whole term. You just throw out this. If you look at this, the term, you just throw out this part here. 2 times 1/2 becomes 1. Do the same thing here. So you just left with this term, but you have to take the derivative of your theta 1. So you need to times r. Okay, for theta 2, for the theta, sorry, this is the one. For theta 2, then you do the same thing, 2 times 1/2 k, write the whole parenthesis. For theta 2, you have to times negative r. So what you have here, so you have kr and the whole thing, and then you have negative r and the whole thing. Okay. So, oh yeah, you don't have here in terms of k r2 theta 1, you just have one expressions here. Yeah, because your x1 is this side here. You don't have anything k with x2 here. All right, so once you've done, you add all the terms up. So you get these 2 expressions. Or equations, and you can rearrange in the matrix form. Okay, substitute, put your assumed solutions, and then get your characteristic equations. Okay, get the determinant. So that's how you get the characteristic equations. And you can solve for your omega 1 and omega 2 using calculators. Okay. After that, you can get your mode shapes. So the way we write your mode shapes is just get the first equation, get theta 1 equals to 1, calculate what is theta 2, add your first frequency, which is 2.2390. Do the same thing for second mode shape. Theta 1 equals to 1, get what is your theta 2, add omega to 7.3464. Just substitute in there. Yeah, so you get this expression. So it should be fairly easy. It's just when you have the problem, you just identify the elements and write your kinetic energy and your potential energy, and also identify if you have damper, then you have release dissipation function. All right, I'm done with that. So make sure you know how to solve all these problems. You're gonna have a quiz. So maybe this time for the quiz, you're gonna have to um, do it something like this. Yeah, it'll take a bit of time, but hopefully you can finish the quiz. I think once you know the steps and it's fairly easy to solve the problem, you know. Although maybe the figure is quite complicated, you can still solve the problems. All right. Any question? I'm done with the materials.
Okay, madam.
Yeah.
For the quiz, it's one question like this.
Yeah, I'm planning for you to submit uh, apa? By calculations like this. Yeah, maybe I make it a bit simpler, of course. Yeah, but this time will be calculations. Okay.
Okay, madam. Thank you.
Right. So make sure on Friday you come on time. And then after that, we also have tutorials this week. We're gonna take a look at other problems related to this as well. Okay, so if no questions, that's all for today. So thank you so much. So have a good day. And I'll see you during tutorial, yeah?
Okay, madam.
Okay,
Thank you.
madam.
Have a good day.
Thank
Thank
you.
you, and have a nice day. Stay safe.
Thank you, madam.
Yeah,
Welcome.
madam.
Thank you.